Okay, hello everyone. Today we are presenting our work from Lab 6. I'm Fei Huang, and here are my teammates.
Hi, I'm Minjin Huang.
I am 胡志鹏.
And first, this lab is focusing on high performance computing with CUDA. So first, our first step is to establish a baseline performance matrix. We do this by implementing a standard matrix multiplication algorithm in C to run on a CPU. So here is our code, and then we run and compare and run it one by one. After that, we try to write a script to automate this data collection, and then we run this script to get the result. So I'm gonna show you how we do this. So first, we need to compare the Lab 6. And then we can automate the data collection progress to by using the script. And then we can get the result. The whole process for CPU takes a really long time, so we just wait here and move on to our lab result. This script will output the following output the generation to generate the CVS file, which we already have it, and the result are here. So now we can move on to GPU acceleration using CUDA. The goal here is to parallelize the matrix multiplication task by offloading the computation to the GPU. The core idea is to have each thread on GPU calculate a single element of the output matrix C. So first, we need to make sure that our computer install CUDA toolkit. So first, we check CUDA version on local computer supported, and then we choose version 13. Next step, we write the code for the CUDA program, and then we also write the script to automatic generate the results. So I'll show you how we generate the results. So we compile the GPU program and then generate using the script to generate the result. As you can show, the GPU is much faster. So here is the result we get from both CPU and the naive CUDA. So the performance improvement on GPU is massive. For 2048 times matrix, the execution time dropped from over 80 seconds on CPU to just 0.022 seconds on the GPU. This represents a speed up of over 3,500 times. This demonstrates the incredible power of GPU's parallel architecture, which distributes the workload across thousands of threads to overcome the computational bottleneck faced by the CPU. So we moved on to the step 3, running the CUDA on Google Cloud. So first, we need to create the GPU instance on Google Cloud, which includes 8 CPUs and 13 GB of memory. So here is our instance on Google Cloud. Let me show you. And then we run, we can. So we also need to install CUDA toolkit on our GPU instance, and then we check the version. And then we also write an automated script to generate the data. So I'll show you how we get the result. So first we need to upload our code, which I think I already uploaded from the local device. So let's just move on to the compiling. First we run the code and then we generate the result data. We generate the data. And then we capture the data. So here is the result running on Google Cloud. So here is the table for performance comparison between among three tools. So it shows the cloud-based T4 GPU also provided a massive speed up over our baseline CPU, achieving a speed up of over 1,018 times for 248 times matrix. However, an interesting comparison here is that a customer-grade GPU design sometimes our local device running the speed is higher than cloud GPU. So it highlights that not all GPUs are the same. So here is our work for first three parts. So I'm going to pass this to my teammates.
Okay. So I'm going to share my screen. So, hi. So I will go over my work from part 4 to part 7 of the CUDA laboratory. And the main goals of this lab were to optimize GPU matrix multiplication using shear memory and tiling, and to analyze performance against the two bloods and the NVIDIA's official high performance BLAST library. And third, we to build a shared CUDA library that can directly used from Python with CTF. Let's start with the optimization part 4. Part 4. So in my file, as you guys can see, the matrix multiply.cu, and I implement a kernel called um, menu tied kernels. It is the optimized version of the matrix multiplication that used shared memory to reduce the numbers of the global memory access and improve the performance. So the key idea is here. So in the naive CUDA version, every thread calculates one element of matrix C by repeatedly reading values from global memory. And that's very inefficient because global memory is slow and every thread reads many as the same elements. So the solution is to divide a matrix into small tiles and let each block load one tile from A and one from B into shared memory, which is much faster and allow data reuse among all threads in the block. So back to the kernel declaration. So we use the tile with 16 and the global void the type of the return function. So here the tile width define the size of each tile, like 16 multiply 16 in this case. And this means each thread block has 256 threads, which is a good balance between the shared memory use and the occupies. And then we go to arrive at these two lines, the shared memory allocations. These two shared array stored a tile of A and a tile of B that are reused by all the 256 threads in the block. Instead of each thread reading data from global memories multiple times. We read once per time and into the shared memories. This is a key performance optimization. And then we have some thread and the block indexing. So each thread is mapped to one element of the output matrix. And this combination of a block and thread indicates index ensure that the grid covers all the elements of the output matrix. And and another main point is the tiny loop. So this loop moves along the k dimension in step of tile width. Each iteration loads one tile of A and one tile of B into shared memory. And the boundary checks make sure we don't read outside the matrix when the site isn't exact the uh, the multiple of the tile size. So and also we the um, the sync threads here. So this one is ensured all the threads finish loading before all threads use the shared data. So I think it is the R4. Uh, also, and also the when writing the output, we finally each thread writes it and it's computed a computed value to the global memory, and the boundary checks avoid invalid writes at the matrix edge. Oh, and also let me mention this one. So the multiple accumulate step. So every thread multiplies one row from DSA, which we write AS in here. So with one column from the BS to accumulate this result. After that, the single thread is called again to make sure the current tie has been fully used before the next tie is loaded. When it's faster, so this design dramatically reduced the global memory traffic because each tie of A and B is loaded once and reused many times. That means few memory transactions are much better use of the GPU parallel architecture. So in my test, the optimized version was about 33 to 4 times faster than the naive CUDA's implementation for the large N. And we can show the table here. So, and let me test my code here. So we have the command here, VCC and O3, which are mhm. Since we have included the part 6 in my file, so we need to add the the Q the tubulus. Okay. Um, let me text. I want to with 5 times. So I design my function and the function um to repeat to have a repeated test. Since each test has some float values and we get the mean value from the multiple tests, we'll get more scientific result. As we can see, the CPU was using the zero point 0.2 second. The naive CUDA used 0.2 ms, and the tied CUDA, which is the shared memory, only used 0.17 ms. And also we can test that the E1024. Okay, so now the CPU used 8 seconds, and the naive used 29 ms. So that's weird. So let's test again. Okay, so it's much more standard. So the CPU used 8 seconds. The type CUDA is more faster than the naive CUDA. So you show the performance. Okay, so this is part five, the performance compression. There's a little like the arrows between the my table and the real-time numbers. But true is true, the optimized CUDA is much faster than the naive CUDA. And now we arrive at the part six using the QBus. So now, and also let me show my code first. So, okay, so the image is optimized matrix multiplication library. Okay, so we at first we follow the instruction. We creating the handles and the parameters. So this will handle initialize the qubits, and the alpha and beta represent the formula. Um, the and since we want C equals to the A multiple B, I set the alpha equals to 1 and the beta equals 0. And this one is the CUDA, the Q plus function calls. So the single card perform the entire matrix multiplication on the GPU. So why B then A? We can see the little trickies here. So the Q plus assume the column measures orders like the fortune, but our C and the NumPy's matrix use row matrix orders. So we pass B first and then A to produce the correct result in row measure logic. This is common and an important trick when mixing Q plus with C or Python. And then we do the copy and clean up like the CUDA memory copy and the CUDA the destroy. After the computations, we copy the results back to the host and destroy the QBLAS handles. In performance test, the QBLAS was about like much faster than the previous one, the tied kernel, the shared memories to that, because it's used the deeper register blocking and the memory prefetching, and some called like tensor coin acceleration. So still, my handwriting versions achieve roughly, I think that's like 17 to 80% of the QBLAS speed, like the a strong result for the customer kernels. And now we create this first seven. So we creating our shared library and using this in Python. So the first step was to make the optimized CUDA code access from Python. So here we only test the shared memory part, not the Q plus part. So here we use the external C. Here we explore function for the C tab on Windows. So it's we use here is prevent the C++ name manually and allowing Python to find and call this function by name. So inside this function, I allocate device memory for A, B, and C with the qdom mem block, and copy and B from the host to the device, and then launch the optimized tied kernel, copy the result back to the host, and in the end, we should free the GPU memories. So these functions wrap everything so the Python can call it easily. And then we can build it and test it. So in Windows, we use the shared. I believe we use the shared, right? In Matrix, I don't. It's LLDDL. Okay, so we have created a word ELL, and then we can pass this library into our function code. So we in here we in Python it's a Python file. We use the syntax to load the library. And why also I want to mention that why we use a shared in here is we told computers that we are creating a library, not the executing file. So and here I load a share memory and specify the function argument type. So this ensure that the NumPy passes raw memories pointer in the correct format expected by the CUDAs. I think it's called, which is the 1D contiguous array of the float 32. Uh, and also we can test, test the conduct. Okay, we can see the Python call to CUDA share library and then finish in 0.1333 seconds. And all the we specify the n equals to the 1024. So I flatten the we flatten the array is the RVVL because my CUDA kernel access element linearly. So and the final line checks the correctness, the maximum absolute error is used around like the one year -6, which is confirm the numerical accuracy. And also in the end, so why this is important? So this step demonstrates how the low-level CUDA kernel can be exposed high-level Python and combining the performance and the usability. So it allowed Python users to benefit from GPU acceleration without writing any CUDA code themselves. Okay, now, so in part four, we implement a shared library, a shared memory type kernel that will use the data efficiently and reduce the global memory traffic. And in part six, we use the QBLAS to benchmark against an image specs implementation and analyze the performance gap. And the next part, we wrapped our kernel into a shared library and successfully called it from the Python using CTAP. So we have demonstrated the future journey and from the raw GPU optimization to professional grade performance analyst, and finally to high-level software integrations. And now I will pass to my teammate for the second, the big part. Thank you.
Okay, now let me share my screen.
Yeah.
Okay. Uh, Now the objective of this part are implement a 2D convolution function on CPU and port the convolution to GPU, which means CUDA, and package the CUDA function as a shared library that can be called from Python. And now we know convolution is computing each output pixel as a weighted sum of its m multiply n neighbors, and different kernels produce different effects. So, which three kinds of filters: blur, sharpen, and edge detection. So, blur is averaging neighboring pixels to reduce noise, and sharpen is emphasizing differences to enhance edges, and edge detection is we call general Laplacian is detecting rapid intensity changes to highlight object boundaries. And uh, now this is the C file, and the CPU implementation is using these two header files to read and write images and implements three kernels. And we can download these two files from GitHub. And this C file takes an input image, applies the filter, saves the output, and prints execution time in seconds. And this is the core convolution routine. Now we can see the pad defines the neighborhood radius, and the out-of-range indices are skipped, and the adding 128 is to make negative edges visible. So this is the three kinds of filters. The blur is equal with normalized by 1 over n squares, and sharpen is subtracting surroundings average and boost the center, and Laplacian means center positive, others negative, and the sum equals 0. And now so we compile this file and we can run this file. Oh, the this is the CPU folders. And now we have these three pictures. This one is 256 multiplied to 156, and this is 512 multiplied to 512, and this is 1000 multiplied 1000. These three pictures, and we can use the cameraman one. So the first number 5, we can use 3, 7. The odd numbers means the convolution kernel, and the second number means the filter, the kinds of filter, and the third one means the runtimes. Now let's use some other. And this is the output. And we test many tests, and the output is here's all the output. Now this is the CUDA file. In CUDA file, the convolution was ported to the GPU, and each thread computes to 1 pixel, and thread coordinates are computed from block IDX, block theme, and thread IDX. All threads execute the same logic concurrently, and the CUDA event elapsed time measures both kernel time and total time, so we can see two outputs. And as usual, this the three kinds of filters. And we can also do the test. The folder is GPU. And we can test the another one. You test the dog. Yes, and this is the output. This is the total time, and this is the kernel time. And we can also see the test output. These three. The third part is compiling the CUDA code into a shared library. The numpy arrays unit 8 store image pixels and pass directly to the CUDA function to receive processed output and timing information. The C types is to load the CUDA shade library, and we define the archetypes so Python and C types can match. These are the parameters. And this is our 3 implementation files. Now we can also do the test. In this folder, yes, do the test in this folder. We've already compiled this file to shared libraries. So, oh, now we can see the performance is showed in this Excel file. Okay, now let's move to the
The final part.
deliverables.
Yeah. So in the final part of our analysis, we compare our customer-written CUDA kernels against NVIDIA's high-optimized industrial standard QBLAST library. QBLAST provides GPU-accelerated routines for basic linear algebra, and we use its function for single precious matrix multiplication to see how a professionally turned library performance. So for the first part, we provide all the source code, and which is not showing in the report is provided in the attached folder. For the second part is a graph. So plot one is about executed time with compare matrix size or implementations. So this long scale graph reveals the massive performance gap between the CPU and all GPU methods. It also clearly establishes QPlus as the fastest implementation, significantly outperforming our customer kernels. So graph one is about the uh, GPU execution time compare matrix size. So this linear scale graph isolates the GPU methods, showing our tailed optimization improves upon the naive kernel. However, it also highlights the superior scalability of QBLAS, whose runtime grows much more slowly for large matrices. So we can so for the all the conclusion we move to the third part report. So this part, the third part is mainly taught the how outcomes and our observation of this lab, which is GPU performance skills far better than the CPUs. So the performance gap as matrix size increases, the performance gap also increases. The initial data transfer overhead is significantly for small workloads, but becomes less impactful as the problem size grows. This explains the racing speed up factor. So our tiling optimization provided a consistent about 1.3 times speed up by reducing memory access, confirming its value. However, the professional turned cubeless library proved vastly superior, demonstrating that using a specialized library is the most effective storage for common tasks. So that's all of our observations for this slide. So that's all. Thank you.
Thank you.
You.
Bye.